we're going to start off by looking at 3.7. And it has, the technique really in this section is using the graphing calculator to solve systems graphically. So what we're looking for is an intersection point. Remember, when you are solving graphically, the calculator can only do two-dimensional graphing. So if you are trying to solve for more than two variables, graphing is probably not the way to go. Okay? Even if you have something that could do 3D graphing, it's going to be kind of challenging. We use algebra at that point usually. All right, so we're going to stick with solving two equations with two variables. Those are the kinds of systems that we're going to look at in this section. When you are solving a system, you need to give me two answers, one for each variable. And you can represent your answer either by writing them as two separate values, or you can write your answer as a coordinate. Okay? Because graphically, the answer is where the intersection is. We could have more than one intersection, especially if we're dealing with shapes that are not lines. Think of a parabola and a line. There would be two solutions where they cross. Or there could be. There could also be one solution or no solution. But when we're dealing with lines, how many places can lines cross if they're not parallel?
One.
Just once. Yeah, parallel, that would be kind of a special case. So the idea is to graph it on the calculator, use second calc intersect, and then find the points where they cross. Okay, so I'm not going to spend a ton of time on it. And maybe we'll try one without a calculator, but we're going to go through it pretty quick. Okay, so it says solve graphically. Well, other methods would be substitution and elimination. We're not focusing on those right now. But if I want to solve that graphically, what's the first thing I have to do to each one of those equations? At least on my kind of calculators. Yeah?
Can't make it y equals mx plus b.
Right, you've got to get y by itself. So in the top one, you would have y equals, let's see, that would be negative 2/3. Once I subtract the 2x and then divide by 3. So negative 2/3 x. And I would have
Plus 5 over 3.
5, and then I'd have to divide that by 3 as well. Okay, and the bottom one, I would have y equals, let's see, I would,
3/5.
yep, add the 3 and divide by 5.
And then plus 7.
And then you would have
Plus,
21
fifths.
21 fifths, yeah. Because you'd have 21, and you'd have to divide by the 5. All right, so now it's just a matter of graphing it and seeing where they cross. Okay, so we've got, I would type it in like this, negative 2/3. Let me try that again. Negative 2/3 x plus 5/3. There's other ways you can do fractions, but what I did there is fine. I'll show you another way you could do it. For the bottom one, instead of doing it like I did above, I'm going to do 3x divided by 5. That's exactly the same thing as 3/5 x plus 21 fifths. Okay, I'm going to do zoom 6. I'll definitely be able to see both my y-intercepts because they don't go above 10. And then to see where they cross, second calc intersect. Doesn't matter where I put the guess because they only cross one time. So the intersection point is negative 2, positive 3. There's one way you can write it. Or that way. Same thing. Any questions how I did that? I'm not saying that's the preferred way with that one. You could probably just use elimination pretty quick on that. but the goal in this section is graphing. So. Okay, this is one that be a little bit harder to do with algebra. Might still be doable, depends. We could try substitution and substitute in for y in the top. The problem would be, can we find a rational root? All right. If we could, then yes, we could do this problem. If we can't, then graphing would be the only way that we've learned so far. So I'm going to type these in. Now that's a cubic and it's a parabola. So we could we get more than one intersection between a gap? With a cubic and a parabola, depending on how it looks, I mean, you could have a situation like that. So I think you could get up to 3. That would be the most. But it all depends on what it looks like. Plus 3x squared plus x plus 3, and negative 2x squared plus 5. I'm going to start with zoom 6, but I don't know if that's going to be good enough because, okay, well there's my cubic. The parabola is going to open down because it's a negative 2. All right, and how many times does it look like they cross? Yep. Twice? Okay.
Right.
Why?
There's just one more point that we can't see that's all the way
Yeah, the red and the blue are getting closer together. So you need to set the y min, I would try maybe negative 40. And hopefully we can see that other intersection point. If not, you'll definitely be able to see them getting closer at this point. But hopefully I did it. No, probably not. So I would do maybe like negative 60. Okay, so I'm not going to find all the intersections here. There are 3 you need to do. But again, I'll just review one of them. So there's 1, 2, and now I can definitely see my third one. Okay, if you don't zoom out, you're going to miss that one. So second calc, intersect. Pick a point on the blue and the red. Now, does the guess matter?
I think you're in the kind of in
Yes.
between,
Why does the guess matter?
because there's multiple.
Yeah, there's multiple. So if I want the one on the lower right, I need to put my guess close to that one. And that is 1 of my 3 answers. That's 4.87 for x and negative 42.39 for y. And there's 2 more that you would have to find as well. Questions on that one? Okay, so last one, it says to solve graphically and algebraically. Well, let's do it algebraically. Okay, so graphically was the focus, and they do have you doing it that way, but I think most people could do that, no problem. Just put it in y1, put it in y2, zoom out so you can see everything, and figure out how many times they could cross. How many times can a cubic and a line cross at most?
3.
Yeah, it could cross 3 times. You know, if you had something like this. Could it cross twice?
Yeah.
Definitely, right? If you had a line right down here like this. It just hits it. Could cross twice. Could it cross once? Yep, if you had a line up here. Could it cross 0?
No.
No, can't cross 0. All right? So you just have to find how many times it crosses. Okay, let's do it algebraically. What method would I use to solve this algebraically? Definitely know when we're solving a system, there's a method you can use back from Algebra 1. Yep.
Not the exact right word, but would be substitution.
Substitution. Yep, it's exactly the right word. So you're going to take what y is equal to in one equation, plug it into the other. And when we're solving equations like this, we generally want to get what on one side by itself? Yeah? Yeah, you're going to have to get 0 on one side and hope we can factor, rational root theorem, synthetic division, something like that. So let's do 0 equals x cubed minus 4x. Now, actually, I don't even need rational root theorem because what do both of those terms have in common? Yeah?
3x. Or it's x cubed.
No, they both don't have an x cubed. Because one of them's cubed and one of them's linear. So the linear one only has one x in it. Yep.
Just x.
Just x. Yep. So let's factor out that x. What would I be left with when I factor it out?
X squared minus 4.
X squared minus 4. And now you already have a quadratic and it's factorable. So we can get the answers that way. There's your factoring. And what would be your 3 answers for x in this case? Yep.
X equals 0, x equals -2, x equals 2.
-2 and 2. But we're not done.
I have to go right now.
Yep. No problem. Just sign out for me and you're all set. And if you don't sign back in, that's fine.
Should I give you this?
Nope, you can keep that. We're only half done. What else do I need? Yep. Yeah, I still need all the y's. So let's do all the y's. I'll just make a table like this. So now, take each of my x's, plug them in, and I'll get my y's. Well, start with 0. 0 cubed minus 0 is how much?
0.
0. What's -2 cubed?
-8.
-8. And what did I plug in? Minus 2.
6. Or -6.
-6. And when you plug in 2, 2 cubed is 8. 8 take away 2 is +6. So easy enough problem to solve without graphing because all the answers came out nice and it was factorable. Any question on that one? And if you put them in a table like that, I can see which ones go with which. If you wanted to do coordinates, you could write coordinates as well. So that's it for 3-7. Not much there. Questions on that? Okay. So what we're going to spend most of the time on today is 4-1, which is on what we call rational functions. 4-1 covers 2 kinds of functions: rational, which means fractions, and radical, which is roots. We will not be doing radical this week. The first 2 parts of chapter 4 focus more on graphing. This third section in chapter 4, I think, focuses on solving equations, so it's algebra. And then the 4th section gets to radicals. So we're not going to get to the 3rd or 4th section in this chapter until next academic week. So what is a rational function? Well, a rational function is when you have a polynomial in the top and you divide by another polynomial in the bottom. Remember, the bottom can never be 0. That's important. And what's an example? Something like that. X squared plus 1, that's a quadratic. X minus 3 is linear. If you take a quadratic and divide by a linear, they're both polynomials. So f of x is called a rational function. How about this? If I did 3x to the -4 plus 5x divided by x minus 1. Is that rational? So what are we really asking? If it's rational, then that means the top and the bottom both have to be what? What's the definition of a rational function? It's on the board. The top and the bottom both have to be polynomials. So when I ask you, is that what I just wrote down, rational, ask yourself, is the top and the bottom, are they both polynomials? What do we think? Is the top a polynomial?
Yes. Yeah.
No.
Oh, it's not one number.
Why isn't the top a polynomial? So that goes back to chapter 3. What makes that not a polynomial?
It's x squared.
Remember, we're looking at this one.
Oh, negative exponent.
It has a negative exponent. You cannot have negative exponents in a polynomial. Okay. How about, okay, I'm going to get rid of the negative exponent. What about now? Is that a rational function? Yeah, that's fine. How about now?
No,
Why not?
because it has a decimal.
As a decimal. Okay, you cannot have a decimal as an exponent in a polynomial. So that is not a rational function. Okay, that's also a rational function. It's two quadratics divided. Yep. And there's an infinite number of examples you could come up with. About this. Is that rational?
No.
No, because square root of x, if you remember from probably algebra 2, when you write square root really means raised to the 1/2 power. So if you have a square root, that's like a decimal exponent. So nope, that's not a polynomial either. How about this? Is that a rational function?
No.
What makes that one not rational?
Two imaginary.
Yeah, the 2i. Polynomials have to have real coefficients. They can't have imaginary coefficients. So no imaginary coefficients, no negative exponents on the variable, no decimal exponents on the variable. How about this? Is that rational?
No.
Why?
Before is a negative exponent.
So could I just think of that like this?
Or is it because it's missing an Oh yeah. Fraction.
That's the same thing, right? So is that second one a rational function?
Yes.
Yeah. Doesn't have any negative exponents on the variables, doesn't have any decimal exponents, doesn't have any imaginary coefficients. Numbers with negative exponents are no problem. That just means fractions. You can have fractions in a polynomial. And you can have decimals. You just can't have them as exponents on variables. Okay? So that's perfectly fine. Okay? Remember, that just means 1/4 cubed. Okay? Okay, so domain of rational functions. It is not all real numbers, okay, because it's a fraction. So because of that, you have to rule out any values that would make the denominator 0. So let's try finding the domain of x squared plus 1 over x minus 3. Okay, so first, is that rational? Yeah, it's a quadratic polynomial in the top, linear polynomial in the bottom. Fits all the characteristics of polynomials, we're good. What is the domain in this case? Yeah.
All real numbers excluding +3.
Yep, all real numbers except 3. And can you give that to me in interval notation, but tell me what the domain is versus what it isn't?
The domain is open parenthesis, -infinity, comma, 3, open parenthesis, or close parenthesis, then open parenthesis,
Something first.
parenthesis, or then parenthesis, 3, comma, infinity.
Yep. you go. So that basically is what you said, all real numbers except 3. Yep. Okay, let's check this one. What do you think we're going to have to do first here to figure out the domain? Yeah.
Find the zeros.
Find the zeros. That's what all of chapter 3 was about. Take and find the roots of the denominator. Okay? Once we find those roots, then the domain is everything except those numbers. But that's a quadratic, so we're not going to have to get into synthetic division or anything like that. What can I do to that to make the roots easier to find? Yeah.
Factors?
Yeah, just factor it. So it's going to factor as x and x. You're going to need a plus and a minus. And I would do plus 2 minus 1. Okay. Numerator doesn't matter. Just keep that the same. So tell me it this way, what does the domain not include? I cannot use, yep.
-2 and +1.
I cannot use -2 and +1. You can use anything lower than -2. You can use anything between -2 and 1. And you can use anything above 1. That's a pretty standard pattern when you have to describe 2 numbers that don't work. Okay, any question on that? Okay, this one. It's kind of the same thing, so I'm not going to write the domain again. It's already factored. Just tell me the 2 numbers that you can't use. Yeah?
2 and -4.
2 and -4. Yep. So if you just change that answer up above slightly, bless you, you'll have the correct answer. Okay, so it's 2 and -4. Any question on that one? Numerator has no effect on it. You don't even have to look at that. The numerator would have an effect when you start to sketch it, but if you're just finding domain, don't worry about the numerator. So the simplest rational function that we can draw is 1 over x. Okay, that's called the reciprocal function. And again, it's considered the simplest rational function. It's just a constant in the top and a linear polynomial in the bottom. So let's graph it. And first of all, you're going to notice that it does something that's a little not quite right. Okay, so let's look at that picture a little closer. What do you notice when you look at that I'm probably going to say is not quite how it should be drawn? Yeah? Okay.
The line never hits 0.
Okay, that's okay. It does never hit 0. We're going to talk about that. So it does get closer and closer to the x-axis. I actually think it did a good job drawing it left to right. I think that's okay. Yeah?
It stops.
Yeah, looks like it just stops. It shouldn't do that. It's because it's getting so steep. The calculator can't draw things that are perfectly up and down. And it's not perfectly up and down, but it's getting pretty steep. This part should really just keep going down. And it's also getting closer and closer to the y-axis without touching it. Does anyone remember what we call that? A line you get close to without ever reaching? Yeah. Asymptote. So we're going to talk about a couple kinds of asymptotes in this graph. Okay, so there's our picture. And I want to know what happens to the y value as x approaches infinity and x approaches negative infinity. So I want to know kind of the behavior of the y value as you head to the right and to the left. What's the y value getting close to? Yeah, it's approaching 0. We've never had n behavior approach a number, and that's because we haven't studied rational functions yet. When we had end behavior with polynomials, they always approached what? Either this or this as you went left and right. Yeah?
Infinity and negative.
Right. Polynomials always approached infinity or negative infinity. This is approaching a number, not infinity. As you head to the right forever, y is getting closer to 0. And as you head to the left forever, y is also getting closer to 0. Because we're getting closer and closer to the x-axis, and we are never reaching it, the x-axis is a horizontal asymptote. And the equation for the x-axis is y equals 0. Now, if you weren't sure that it was an asymptote, what would be a good value I could plug in for x to check and see what the y value is? If I wanted to examine the behavior as you head right. Anybody? Yeah.
0.
No, 0's near the origin. I want to head right. I want to start heading to the right and watch what happens to y. Let's say you don't have that picture. All I have is a table to look at. Yep.
To the right, a y, unevenly lower.
Well, that's what I want to check on the calculator. I'm going to pretend I don't know what it looks like. So what would be a good x value to test?
10.
Sure, we could check 10, see what happens. Okay, we get 0.1. What's another good x value? Let's keep going. Yeah,
50.
so we could try 50. All right, I'm even lower, 0.02. We could try 200. Now I'm at 0.005. I can see that it's getting smaller. And I'm all the way at 200 and it hasn't reached it yet. So it's probably not going to reach it. Okay. 500, I'm at 0.002. Okay, now I can definitely see it's getting close. But even if I keep getting bigger with x, it's not reaching it. Eventually, it's going to run out of decimals and it's going to start using scientific notation. Now that's 0.0002. But it ran out of decimals, so that's why it shows it that way. Okay, but it's just getting closer and closer. And you could check the same thing when you go in the negative direction as well. So to find a horizontal asymptote, you examine what happens to y as x gets bigger and bigger in the positive direction and the negative direction. In this case, the same thing happens. As x heads in the positive direction, y gets close to 0. As x heads in the negative direction, y gets close to 0. It's not always the same, but in this one, it is. Okay. And the other thing to understand about asymptotes is they are lines that you don't cross in these kind of graphs as you head towards infinity. You can cross it near the origin. That's fine. An asymptote doesn't really tell you what's happening when x is a small value. It tells you what's happening as x gets to be bigger and bigger. You usually have something you approach and never cross. There are some graphs that can cross or kind of oscillate around an asymptote. We haven't talked about trig functions yet, but if you had a trig function with a constantly decreasing amplitude like that, it's kind of oscillating around an asymptote, so I'm not going to get into that. We're just going to look at lines that as you head to the right, they eventually reach a point where they don't cross the asymptote anymore, and they just get closer to it. Okay? So that's basically how you find it. You can use your calculator, start plugging in some bigger values for x, and tell me what y looks like it's getting close to. Okay, so let's try this one. Find the horizontal asymptotes of 1 divided by x plus 2. Now, you can use the table, but this is a simple enough problem. You really don't need it to figure out what's going to happen. Look at that fraction. As x gets bigger and bigger, like 1 million, 10 million, 200 billion, right? As x gets bigger and bigger, what's going to happen to the number that's inside that box? Yeah,
It's very small.
it's going to get very small. And what's inside this box is going to get very close to what? Very close to 0, right? It's going to get very close to 0. Like if this was 200 billion, that's 1 divided by 200 billion. It's almost 0. It's very small. If you take a number that's almost 0 and you add 2 to it, what would you basically get? Yeah? 2. You get a number just a little bigger than 2, like 2.00000000001, right? Just a little bigger than 2. So in this case, the horizontal asymptote would be the line y equals 2. Now, if you check what happens as x heads in the negative direction, like if you do 1 over negative a million, that's going to be a number that's very, very close to 0, but negative. So when you add 2 to an extremely small negative number, you get something like negative 1.9. You get something like 1.999999999. Okay, it's still getting very close to 2, just coming up from the bottom rather than coming down from the top. So it's really just like that graph, except it's shifted up vertically 2 units. How about here? What's going to be my horizontal asymptote for that one? Yeah. Yep, y equals negative 3. And if it was multiple choice, yes, I would give you a choice of x equals negative 3 and y equals negative 3. What kind of line would x equals negative 3 be? Yep. Well, the slope is undefined, but it's a graph you could draw. But what kind of line? Yeah,
Vertical.
that's a vertical line. So right now we're talking about horizontal. So you need to make sure you get the letter correct in front. Any questions on how we found the horizontal asymptotes there? That's going to be important when we get into sketching. Well, I mean, if you wanted to sketch that, the first thing you do is sketch your horizontal asymptote. That's y equals 2. And you can plug in some different values and see what happens. But you can't plug in 0, because that would cause you to divide by 0. So I would pick values like 1, 3, 5, 10, right? Plug them in and see what you get and plot the points. That's the easiest way to do it. So 1 over x plus 2. Okay, just get a few values. Not that big. 1, 3, 5, 10. Now you've got some coordinates that you can plot. Okay, you've got 1, 3. We've got, let's put that over there, 3, 2 and a third. 3, 1, 2 and a third. When I get to 5, I'm at 2.2. So basically it's curving down and it's just getting closer. I might want to check like 0.5. If you plug in 0.5, 1 divided by 0.5 gives me 2, plus 2 is 4. So what's going to happen is as x gets close to 0, we haven't talked about vertical asymptotes yet, but it's basically going to curve up like that, and that's going to continue like that. Okay. And same thing in the lower left section. The graph with the plus 2 is exactly the same as this graph right here. Oops. Just shift everything up 2. That's all that's happening. Something kind of like that. I might not have my curve in the exact spot. I'd have to plot maybe a couple points around -1, -2 to figure that out. But that's the idea. Okay, are we gonna? No, we're not gonna look at that one. Okay, so let's look at this graph again. So same graph that we just did. This time I don't want to look at what happens as x approaches infinity. I want to look at what happens as x approaches 0. As x gets smaller and smaller and smaller, like 0.1, 0.0001, 0.000001, very, very small. What happens if you take 1 and you divide by an extremely small number? What do you get? Or what is the value get close to? If you take 1 and divide it by something extremely small. Oh, Whalen?
It's a bigger.
It gets to be bigger, right? How big is it going to get? Like, let's say x was like 1/1,000,000th.
It'll be.
What's 1 divided by 1/1,000,000th?
Right?
Yeah, a million. Right? It's going to be a million. So if x is a millionth, y is going to be 1,000,000. Okay? So if x gets even smaller, if x is a billionth, y is going to be a billion. So what is the y value approaching as x continues to get smaller?
Infinity.
Infinity. Yep. So as x approaches 0 from the positive side, let me get the graph back up here so we can look at that. Let's get rid of that. There we go. As x approaches 0 from the positive side, that means start on the positive side and start approaching 0, but stay on your graph. Look where you're going. You're heading up to infinity. Now, what about as x approaches 0 from the negative side? So here's your negative side. Start going towards 0 and follow where the graph takes you. Yeah?
Negative infinity.
Negative infinity. Yep. I guess I erased that. Just down there. So when we have that behavior where as you approach a value, it generally increases on one side, could increase on both sides. But in this case, one side goes up, the other side goes down. That behavior usually indicates a vertical asymptote. Can everybody see through green and write it down? Okay. One second. The smart notebook thing, I think I pressed something and I caused it to freeze. Sure. Let's go back. Right here. Okay, so as x approaches 0 from the negative side, it heads down forever, and that's a vertical asymptote. Vertical asymptotes are pretty easy to see on a graph, because that's where you all of a sudden you see something that's spiking up, or as you head in another direction, it could be like plummeting down on the other side. Okay, so they're very, very easy to see when you graph them. They're also pretty easy to find algebraically. If we look back at our graph, what value would you plug in here that would cause this to be undefined? Yeah.
0.
0. So if you can figure out the values that cause your rational function to come out to be undefined, you pretty much, most of the time, have found your vertical asymptote. There's only one catch with that. If the numerator and denominator have a common factor, then you will not get a vertical asymptote. If I graph something like this, yes, 3 causes an undefined value, but it would not be a vertical asymptote in this case because there's a common factor. Does anybody remember what happens on the graph when you have a common factor at the number that causes you to divide by 0? something you almost can't see on the graph, but we talked about it. Yeah?
Doesn't it become discontinuous?
There is a discontinuity. Vertical asymptotes are also a discontinuity. They're just a very obvious one. This one is not obvious when you draw it. Does anybody remember what we called it? It's the same day we studied step functions, and we did continuity, intermediate value theorem, and end behavior asymptotes. I think it was 3.2. I think. What do we call it when there's a common factor in the numerator and the denominator? I'm looking for the word we use to describe what would happen at 3. Yeah?
As a whole?
There's a hole. Yes. There's a hole in the graph. So if I asked you to tell me the vertical asymptotes of this function, you would say there are none. There will be a hole at 3. Now, if I did that and I said, what are the vertical asymptotes? Now, the numerator and the denominator don't have any common factors. So we could say that there is a vertical asymptote when the denominator is 0, which is at 3. Okay, so that is an important catch. You have to make sure your numerator and denominator do not have any common factors. As long as they don't, the zeros of the denominator give you the vertical asymptotes. And when you write the equation of something vertical, what letter do we use? Yeah, X. Yep. Horizontal we use Y, and you cannot switch them. If you switch them, it's not right. Okay, so find the vertical asymptote of this equation. Okay, any common factors between the numerator and denominator? Bella, what do you think? No. Nope. So then all we have to do is figure out that, and that's your answer. So can you tell me what the vertical asymptote would be?
2.
And can you give it to me as an equation?
X minus 2? Or, I don't know.
Yeah. So I'm looking for an equation that, like, if you said graph this, I would graph a vertical line at 2. Yep.
X equals 2.
X equals 2. So that's the equation of the vertical asymptote. How about here? What's the equation of the vertical asymptote? Yeah.
X equals negative 1/2.
Not negative 1/2. Because if I plug in negative 1/2, that doesn't give me any issues in the denominator. Yeah?
Or the x equals -3.
Yes. Remember, the vertical asymptotes are the values that would make the denominator 0. So in that case, it is -3. Yep. What would be the vertical asymptote now?
Negative 3.
Still -3.
Oh.
Making it -11 didn't change the vertical asymptote. What did it change?
It changed.
Yes, it did change the horizontal because now, well, we talked about that. But yeah, the horizontal just changed, but not the vertical. So this number affects the vertical, this number affects the horizontal. Okay, so this one says find the horizontal asymptotes and then describe the transformations. Okay, so just in case we need a refresher on transformations, let me write something kind of generic here. Each one of those letters represents one of your shifts and stretches. What does adding inside the function do? Which way, how does that affect your graph? Addition, but it's on the inside. Yep.
It shifts your vertical asymptote.
So horizontal shift, horizontal stretch, vertical shift, or vertical stretch.
Vertical shift.
No, adding or subtracting a number on the end is always the vertical shift.
Horizontal.
Since this would affect the vertical asymptote, this is a horizontal shift. What about B? It's still inside the function, but it's multiplying instead of adding. Yep,
Horizontal stretch.
that's your horizontal stretch. And whether the C was out in front, sometimes you might see it that way. You could see it out in front, or they could multiply the C in and then just put it on top. But either way, what kind of transformation is the C? Yep,
Vertical stretch.
vertical stretch. And if the C or the B is a negative value, what does that cause your graph to do?
Because of the flip, right?
Causes it to flip. B is a horizontal reflection if it's negative. C is a vertical reflection. So it's really the same kind of transformations we studied back in chapter 2 when we talked about parabolas. And the same order applies. That's why I used A, B, C, D. You write them in that order. A, B, C, D. What else? Remember, horizontal is backwards. So if you see like x plus 3 in the bottom, a plus 3 is going to shift it left. A minus 3 would shift it right. Okay. So now, looking at this one, does that one have a single number in the top or a 1 in the top? The one in green.
It is not.
It does not. So that we need to fix it. This is not written in an easy way to figure out the transformation. So we need to do this out. Okay? So divide 2x minus 13 by x minus 5. Okay? So we could use synthetic division. Write down your numbers on the inside. Bring down the 2. 5 times 2 gives me 10. Add those up. What's the negative 3?
Remainder.
That's my remainder. So 2 is my,
Top. Or it's your quotient.
that's my quotient. So when we write this, we're going to write down, let's see, start with the remainder part. When you do long division, just a quick refresh on that, 17 divided by 3. What's the quotient there?
15. 55.
5. And what's the remainder?
2.
2. So the way you write your answer is quotient plus remainder over original denominator. So the answer to 17 divided by 3 is 5 plus 2/3. You're going to do exactly the same thing here. Let's write down quotient, which is 2, plus my remainder, negative 3, over my original denominator, x minus 5. Now, if I just rearrange that a little bit, negative 3 over x minus 5 plus 2. That's exactly how it needs to look to describe the transformations. It's perfect. What is this minus 5 going to do?
Shift it to the right.
It's going to shift, let's see, right 5. It says right. What's that 3 going to do?
With a vertical stretch of negative 3.
Vertical stretch by factor of what?
Negative. Or by factor of 3.
Factor of
And
3.
Flip.
Now the next thing is to describe the negative, which causes it to
Flip.
flip vertically. So you could say vertical reflection. And the last thing is the plus 2 on the end.
Shifts left 2.
We've already done horizontal.
Oh.
What's the plus 2 going to do?
Up.
Yep.
Up 2.
Shift up 2. Okay, and I didn't actually answer the horizontal. What's my horizontal asymptote here? You can look back. You can, well, I would just look at the what's in the box here. Think of where the horizontal asymptote is normally, and think about which way it shifted. Shifting left and right would not affect something that goes forever left and right. Yeah?
I equals 2.
Y equals 2, perfect. Remember, horizontal asymptote, let this number approach infinity. Tell me what happens. It usually makes this part 0, and then the plus 2 makes it up 2. What's my vertical asymptote going to be? Think about where it would be, and think about which way you just shifted. Yep, 5. That's the zeros of the denominator. Now, you could have found the vertical asymptote without rewriting it, but you would not have been able to get these transformations without doing the synthetic division. Okay. So that's a good place to stop. Which one didn't we do? Oh, the mixture problem. We'll hold off. We'll do the mixture problem tomorrow. So I think 48, A and B, that's the mixture problem. I don't expect you to be able to do that one. So if you get up to 38 on page 22, that's fine. And then on 207, 8 through 10, that's graphing and finding an intercept. Okay, so we're gonna do 48 when we go over the homework tomorrow, if you don't get it.